Alright class, we're going to pick up from where we left off last time and dive into privileges. Um, it is very common for applications to drop privileges to a less privileged state or user ID to, to operate and perform some features. Um, for instance, the code provided here drops privileges. For instance, if this were run as root, UID would be 0, and by setting effective user ID to 5 is changing to a non-root user and then performing some code, which in just this toy example happens to be a vertical function. But demonstrates that um, if this were to be attacked and someone were to pop a shell, it would spawn under the user ID 5. However, nothing prevents an attacker from crafting shellcode that um, makes the same call and tries to restore privileges. Um, set RESUID to system calls allow such functionality, and the following shellcode will attempt to restore root privileges. If any one of these is still 0, it may allow the restoration of root privileges. Um, and you can read up on set RESUID. It won't be on the exam, but it's very important to know this technique. And the shellcode after this simply attempts to spawn a shell, which would hopefully be at root if this were all to work. So before we dive into the rest of the lecture, let's go over some reference slides for shellcode and registers and also process memory space. In 64-bit architecture, instead of EAX, EBX, ECX, everything starts with R, and then there's even more general purpose registers, R8 through R15. And the registers are 64 bits instead of 32 bits, and there's twice the number of general purpose registers. And we're not going to cover Windows shellcode in this class, but it is not like Linux. It is actually exceptionally easy to write Windows shellcode, and the Shellcode's Handbook has a pretty good section on that. I don't think it's in our textbook, The Art of Exploitation, but essentially Windows shellcode involves accessing the provided API for the Windows kernel, which is Win32 API, and the DLLs associated for it. And then you want to load the libraries and get the proc addresses for whatever functions you want to run, and simply just call the procedures. It's relatively that straightforward. The Corelland tutorials, which we suggest later on in this lecture, provide very good introduction to this and are a must if you wish to go into any form of Windows security in this style. So to recap Linux and Windows process space, Linux, the higher memory here is at the top, and the stack grows towards lower memory, and the heap grows towards higher memory. This is where the dynamic libraries are loaded in. You have the BSS segment, you have the data segment, you have the text segment. And for Windows, according to this diagram and from other things that I've found, the stack and the heap are beside each other and they grow apart. And other segments include the .text segment, the data segment, the PE header, and Windows. You also have the process execution block, I believe, and other useful segments. And let's go ahead and dive into heap exploitation. The three subjects we're going to cover this lecture are heap exploitation, format string exploitation, and then executable security mitigations, so defenses. So the most useful resources are secure coding in C and C++. The textbook has some decent coverage of the subject, but there are also some good talks, heaps about heaps, and practical heap exploitation as well. A lot of this section is going to be recap from Lecture 3. And this is an old slide. It's essentially telling you that for each chunk you're going to have metadata on the beginning, metadata on the bottom of it, and that chunks are grouped into bins, and usually there's some form of best fit algorithm to minimize waste, and it's also going to be a doubly linked list. And, well, we've covered effectively the unlink algorithm and how it's exploited in a buffer overflow, and that when you overwrite, it will cause it to segfault, because when it tries to free the second one, it's going to be using user data as pointers, and it's probably going to access memory improperly. So if you construct it so that you exploit the previous and use flags accordingly, you can trigger the unlink to think that, oh, hey, I should coalesce these. The free algorithm to think, oh, hey, I should coalesce these, and that will trigger the unlink macro, which will look at the pointers that you provided, and this is the correct slide, I just pasted it wrong. And it will write a destination, write to an arbitrary destination, arbitrary value. So I suggest you refresh on Lecture 3. It was better explained there. And there are standard C routines for operating the heap in dynamic memory: malloc, free, realloc, alloc, and other ones we've called. There's also BRK, SBRK, memory map, etc. And a very, very simple explanation of this is that if there's any user data that's controlling how much is malloced, and it's being used in some unsafe function to perhaps dictate how much is copied, perhaps an attacker can overwrite something with a very large array or a string. Another simple example, always unfortunately using strcpy in this slide, I should change it, but effectively this allows us to overwrite the metadata for buff2 as it grows towards higher memory, and so buff1 will write first, and then any overflows will write towards the next item, so buff2 will get overwritten. So let's look at an exercise with heap exploitation. All right, class, this is the Heap 3 walkthrough for Protostars challenge exercises from exploitexercises.com. There's two functions here. We are lucky enough to have the source. There's a winner function. Obviously, we have to get here somehow. And then there's the main function. And the main function has three basically strings that are being allocated, put on the heap. And obviously, they're strcpy. That's where the vulnerability is, clear as day. And then they are freed in reverse order, which doesn't really affect the exploitability of this. However, there's no direct call to winner, so we're going to have to find some way with this heap vulnerability to hijack execution. And from our previous lectures, we've already shown how exploiting the unlink macro can allow for the arbitrary writing of a pointer address. So let's play around with it. And if we run it, it's going to exit right away and print dynamite failed. So we're going to have to add a breakpoint, and luckily this thing was compiled with debugging symbols, so we can simply do break on source code line 24, and it's going to break right here before it gets to free C. So if we run it with A's, B's, and C's, we're able to break at that point and inspect what's going on beforehand. So one of these registers is going to point somewhere on the heap in order to coordinate with free to do its job. So let's inspect about 40 hex words X, the first one stands for examine, and then the slash and what falls after it specifies what to format it as. So let's do what is an EAX. So 4C058. We don't see anything, but at the beginning we see 434343, and that's ASCII for a bunch of C's repeating. So we're really close. Let's view a little earlier on it, and it seems like we found some sort of structure here. If you take a look, there's 41s, then there's 42s and 43s, so that's all A's, then B's and C's, and so we found the chunks on the heap. So if we give it a ton of A's, we will obviously see what happens at this point. And it's overflowed all the way into chunk 3. However, the data that we write into chunk B and C gets written anyways, and that just happens to be the order in which things are written. However, if you run this normally, you'll see that we are overwriting some things that the code itself does put in there. For instance, at the very first line, there's a hex 29, and there's 29 here as well. And then before the 4 threes begin, there's another 29, and so on and so on. And these happen to be the metadata for the chunks on the heap, specifying the size of each chunk. So what we want to do in order to exploit the unlink macro is that we need to provide a new dummy chunk header so that when it goes to free not A, but the second one it frees, it's going to trigger the unlink macro because we're going to play with the previous in use flags. And if you remember lecture 3, this should be pretty easy to understand. So what we're going to do is I think the arrows are wrong here. This should be boop. This should be there. I got copied and pasted wrong. There we go. And what we're going to do is have an exploit that looks roughly like this. We're going to take buffer A, and we're going to fill it up with 32 A's, and then we're going to start overwriting the metadata on the heap. So let's give it 2 -4s, which happens to be FC, FF, and then for the second chunk, this first part is going to get overwritten. And so when we enter in B, we're going to put in this data is still going to get written regardless. And what we're going to do is we're going to have a fake chunk header. And it doesn't really matter what it is. So we're just going to have BB, BB, BB. And we're going to have for the destination that we're going to do the arbitrary write and the value that we're going to do the arbitrary write be AA, BB, CC, DD, and then 4433, 2211 respectively. And we're going to see how this behaves when we get to the second free and it encounters this exploit code. So you see that it's seg faulted. Let's inspect the registers after we see what EIP was pointing to. So we're moving EDX into EAX plus OXC, which happens to be EAX plus 12. So we see that EAX is AABBCCDD. That's what we wanted. And EDX is 44332211. This is exactly what I told you guys how the unlinked macro behaves. It's a good indicator that so far is so good. So we now have the ability to do an arbitrary write. Remember that the destination has 12 added to it, so you need to subtract wherever you're at, wherever you're pointing to, by 12, and then obviously when this instruction runs, it's going to add 12 to it and store this value there. So what we want to do is exploit something we talked about in lecture 2, and that is the global offset table. And let's look at the global offset table for heap 3, and we have these various functions that are indicated, that are pointed to by the global offset table when it runs. And first time it runs, it's unpopulated, and on the first call, it gets found in memory. The global offset table is updated and doesn't have to go find it ever again after the first try. So we have our printf and putS, and let's look back at the source code. And we see there's a printf, so let's just make sure that it's there. So let's disassemble main, and we have the original malloc calls, then the strcpy calls. Let's keep going. And we have more of the strcpy calls, and then we have the free calls, and then we have the return. But before that, we actually have putS. And this is one of those tricky parts that you always encounter in exploit development, of dealing with the compiler optimizations. And in this case, whenever printf is called, this compiler, and this is a very common case with most compilers, will actually call putS instead. If printf is called without any conversion specifiers, as you can see, dynamite failed, it's just a static string, it will call putS instead because it's a much more efficient implementation. It doesn't do perhaps the dozens of lines of assembly to look through the strings provided for any format specifier and do the expanding macro that's required to handle it. Instead, putS just statically puts it out to standard out. Very simple. However, this is one of the nuances of exploit development that can throw a lot of people off. So what we're going to target is, despite printf being in the source code, we're going to have to target putS. So let's go back and find the address for putS. That's going to be 0804B128. And then we're going to have to subtract 12 from it, and that happens to be 0804B11C. You can double check the math, I've already done it, just for sake of demo. And so what we're going to do is we want to take, instead of write to AABBCCDD, we're going to write to the global offset table here. So 1C, B1, 04, 08. Remember, little endian, this definitely matters. And let's just leave that for now. It's going to hit the breakpoint. We haven't decided what we want to write there yet, but we can verify that it has worked. 0x, so let's look at the global offset table now. No, perhaps it hasn't. So it's trying to write one of the constraints we see that in free, it's using EAX as a pointer, and if we have it pointing to 44332211, well, that's probably not a valid memory segment for writing to, so it's going to segfault. So we need to give it our actual intended target. And since the goal of this is to run winner, let's see where winner is. So it is at 8048864. So let's put that as the value that we're writing instead of 44332211. So 64880408. And CCCC for string C. We still don't care about that. And let's keep going. See what happens now. Still seg fault. Let's see what's going on with EIP. That looks like the same instruction, and it's trying to take EAX and use it as a pointer. Let's see what's going on. That's winner. So if you're trying to write to winner, that's going to be in the .text segment. And the .text segment is where the machine instructions are, and it is never writable. It is just executable and readable. So that's what's triggering the seg fault. However, let's see if our arbitrary write worked. We have it written on the left side of the screen, so it's 804B11C. And did I type it right? Yep. So what I forgot to do was continue at the breakpoint. So now we've actually hit a segmentation fault, and let's examine what we are writing. It doesn't appear that it is correct. In fact, I'm actually mistaken. We need to add 12 to this. So put S should be at this, and it has indeed overwritten the global offset table entry for put S with the address of winner. However, EIP is still using that value that we're writing as a destination for a write, which is a problem because it's, as I indicated, in the .text segment. So what we need to do is instead use a segment of memory to jump to that we can also write to, because one of the constraints of this code that we're having to exploit is that it needs the value that we write here to also be something that it can use as a destination for a pointer, because in the last stage of the unlink macro, it's going to use that. So what we're going to do is construct an exploit such that we have an op sled, and we're going to point it to the heap. We're going to point it to chunk A. And we're going to provide some shellcode that's going to jump to winner, and it should be pretty straightforward. So what we're going to do is instead of this exploit, we're going to provide it a exploit with shellcode and an opsled, and effectively the shellcode is going to be push the address of winner on the stack and then call return. Return is going to be effectively the same as pop EAP. So if you push something on stack and immediately call return, it's effectively putting that into EIP. It should be noted that on x86, you cannot directly assign anything to EIP. So the compiled assembly for the shellcode, the opcodes are the following. And so 686488080408. This is actually the opcodes for pushing the address of winner. And if we see on the right that the address of winner is printed here, 08048864, and so you'll see that little endian encoding is going to be 08048864, as I said, and 68 is the opcode for the push instruction. C3 is the opcode for the return instruction here, and so this is a pretty concise payload. And so what we're going to do first is pad it with 20 NOPs, which is the opcode for that is 90. No-op, or sometimes just referred to as NOP, is effectively the same as move EAX EAX. It's functionally useless. And what it does is provide you a nice cushion if you're not sure you can precisely target something. If you land it on a very large sequential amount of no operations or functionally useless operations, it will keep executing until it perhaps hits your shellcode that you've landed after it. So what we're doing is having a nice NOP sled, that's 20 NOPs, then our payload that's basically push the address of winner, and then C3, which is red. And as indicated here, here are some just filler bytes. I'm going to play with the filler bytes and show you actually how sometimes following write-ups and other people's exploits isn't so easy, and there's sometimes nuances dealing with the constraints of given code paths that can really be frustrating. The fillers bytes here actually have some significance that are completely omitted in all the write-ups for this challenge. Then what we have is the fake header for this next buffer, this next fake chunk that is used to trigger the unlinked macro to exploit. And then we have chunk B, and we are pointing back to the heap. And we found that simply just by examining the heap and figuring out where to point to. And we are pointing, we are rewriting the global offset table entry for put S with this address to jump back to the heap. And so what happens is when we run it, it's going to print out, that wasn't too bad now, was it? Which happens to be the string printed out by winner. So to dive into this, to recap actually, let's run it again. This is what the heap looks like. We see that at the very top row there is the hex 29, which is the size of chunk A, and then the data is filled with all 90909090, which is the NOP sled. And then here at the end of the second row, you see the payload that we've put in there, and it wraps around to the next row, and we see these garbage bytes 4141, and they keep going. This is partially for alignment, and then we see the -4 bytes, which is FFFFFFFC that we've written here, and that's the fake trunk header. And then after that is the the placeholder, which is the 4242s for the dummy chunk header, and then our destination in the global offset table, and then finally the pointer to point back to the knob sled. And that is essentially the exploit. The rest of it is all fluff. So let's play around with these filler bytes, and if we change them to certain values, it will actually cause the program, the exploit, to fail. For instance, we got a segmentation fault this time, and let's see what's going on. Let's examine what's going on in EIP. It's trying to move EDX into EAX plus 12, and EAX is -4, and I guarantee that memory address is not writable. So I don't feel like reverse engineering exactly why this is occurring from just changing these 6 bytes here from effectively what was 4.1 to CC, which is the trap instruction, which is very, very useful for debugging, and that will probably end up on one of the exams. What is the opcode for the trap instruction? It is CC. So that's something to be aware of, that sometimes your filler data does matter and will affect the constraints of the code paths that you're exploiting. And so when I return it to 4.1s, it doesn't segfault. Anyways. Okay, so we finished that demo. When dealing with Windows, it's important to remember, or rather, it's important to know that processes can have multiple heaps. Each process gets a default one, but in multi-threaded processes, all threads share a common one. But sometimes, if there's a DLL or a shared object, those can create their own heaps to work with. And there's nothing preventing an attacker from creating a separate heap for whatever purposes they want and giving it whatever permissions to read, write, and execute that they would like. There are other heap techniques that you should be aware of. Heap feng shui is presented in 2007 and is effectively the art of manipulating the structures on the heap to align more predictably so that you can more reliably exploit a given vulnerability that happens to manifest on the heap. And so it's a pretty interesting technique that's been around for a while. Another technique we're talking about is heap sprays. Very, very common in browser malware because browsers run JavaScript on the client side, and JavaScript just lets anyone allocate arbitrary amounts of memory, dynamic memory, for whatever purposes they want. So an attacker can just spray the heap with malicious code and hopefully jump in somewhere in that section of the process if he or she manages to hijack execution, and that can make defeating ASLR a bit easier. And we're going to cover ASLR later in this lecture. So let's continue to format string exploitation and have 2 demos on this. Slides here are very much a recap. We covered in lecture 3 at the end of it the flags, the width, the dot precision specifier, the length modifier, and finally the conversion specifier. All of these let you see values on the stack. However, %n is the only one that allows you to write. Nothing will be printed, but it writes the amount of characters written so far to a corresponding pointer located on the stack. For instance, if you have a format string vulnerability where you just print user buffer and you pass it %s's, it's going to read each value it finds on the stack for each %s as a pointer and dereference it and continue until a seg faults or until all the specifiers are satisfied. The above example uses the width specifier to print out not perhaps 32-bit hex values, but as 64-bit or 8 bytes. And this can make, when hunting format strings and mem leaks, can make finding it a little more human friendly. And this will increment, it should be noted, the pointer used to handle the variable amount of arguments by 8 each time, which is the VA list iterator, however it is implemented for given variable argument function that it has the format string variability. You can move it forward by other values, not just 8 or 4, but typically just those. And this technique lets you view arbitrary memory locations. What's happening is it's pushing the pointer forward until %s starts looking at the own string here, and then it dereferences this value on the stack as a pointer to a legitimate string address and prints it out accordingly. So it'll print out the string at the address 04E5F5DE. And this above is little endian. We've talked about writing to a memory address, and effectively using the same technique, instead of a %s here we use a %n, we'll write the number of characters written so far to the address provided here, assuming this all works out correctly. And you can use a width specifier to increase the number of characters written so far to specify exactly what number you would like to write there. But it only works well for writing small values. So we need to explore how this can be used, and perhaps with the length specifier, to pull off various format string exploits. And we're going to start with the Protostar Challenge Format 1, and here we go. Format 1 challenge demo from Protostar from exploitexercises.com. On the left we have the source code, and there are two functions. There is vuln and there is main, and you can see that main takes in arguments and it passes the first command line argument to vuln, and it takes in a string, it prints out the string, and this is clearly where the format string vulnerability is, and it's asking us if we have modified the target, and that's the goal, to modify the target. The target variable, however, is here, global variable, and this is going to be in the .bss segment, which is far away from the stack. So let's throw a bunch of format strings, conversion specifiers at format 1, and we can see that it is indeed printing out memory from the stack. And what we want to do is pass it a string and then be able to find where on the stack this is. And so we're putting periods here so that we can count how far it is. And you can see that if we're looking for the hex representation of AAAA, it should be 41414141, and you don't see it. And what we can do is, instead of just passing a ton of %x periods, we can do something a little more clever. Let's use some bash scripting to give it a range from 1 to 200, and we can tell it to directly access variables on the stack um, in this fashion. So we have this for loop, and what we're going to do is we're going to run format1, and we're going to give it 4 A's, and we're going to give it the iterator that we're going to iterate over, and it's going to start from the first value, then go to the second, third, fourth, sixth, seventh, and then escape a $ symbol so it prints out correctly. Most of the time when you have trouble with format strings, it's probably because you're not formatting something just quite right. And so we want to print out values in the stack. And what we want to do is filter out cases. We can just run this as is. Oops, forgot to do. And you see, we need to filter out all this information. Like, we're not interested in seg faults. So get rid of the done, get rid of the semicolon, grep for when it's printing out the representation of AAAA. And didn't find any. And this may be a padding error. Let's, not a padding problem, I'm sorry, I meant to say an alignment issue. Let's add a little statement that evaluates whether or not this grep matched anything. So if it's true, then we're going to echo what the value of I is. We're going to break this loop. We're going to end this if statement, and then we're going to be done. And so this runs. It doesn't find anything. It doesn't echo out what I is. So since it's likely an alignment issue, let's try putting stuff at the beginning. So I'm going to just put 1 byte in front of the 4 A's that I have. Run it. Nada. Nothing. Let's try another one. Nothing. And the third one, likelihood of this working is ever decreasing. And the fourth one is at the point you should give up on alignment, because now you've come full circle if you're working with a 4-character string anyways. So let's try adding it on the end of the 4-character string. 1 did not work. Add a second one, and there we go. So we did get it to align right, and it happens to, on the 124th hex value, print out 41414141 when given a conversion specifier to print out a hex value on the stack. So the reason it's so far up the stack is that in Vuln, when print is called, print is a stack frame deeper in Vuln, and Vuln is a stack frame deeper from main. So the argument for this are actually a bit higher than that, and that's why it's effectively so far up the stack. So what we need to do is, now that we know where on the stack our input is going to be, we need to now use the %n conversion specifier to overwrite target here. It doesn't matter what we write it with. It just has to have some value written to it. So let's look at the symbols, find the target. It's going to be at 3.8. Okay. So what we're going to do is format 1, and I'm going to pass it in through Python so it prints nice. We're going to give it the destination, so that's 960408, and then we have 124 as a magic number, and we're going to give it n here, and didn't work. Maybe this was the trick. Oh, we forgot the alignment issue. So 08, we need BB here. And boom, we've modified the target. That means that this format string exploit successfully wrote some value to target all the way up at the BSS segment, which means that this has been a successful exploit. So that was a rather simple demonstration of writing an arbitrary yet small value to a specific memory address. Whether or not it's on the stack or the heap, we managed to target the BSS segment. It just happens to be, as long as the memory segment is writable, you can use that technique to write to it. However, what if we want to write a larger value, perhaps a pointer to an arbitrary memory address? Well, what we're going to explore in the next demo is a technique that uses multiple writes to write small values, and each write, doesn't matter what is written in the more significant bytes, is then followed up by a write starting at the next address, in which the least significant byte of it is used to write at that specific byte, and then so on. It doesn't matter what follows it, but is followed by another write that cleans up whatever's past it and uses the least significant byte to set the third byte, and then so on for the fourth byte. What happens over 4 writes is that by shifting 1 byte over each time in such a manner, you're able to control a pointer address at an arbitrary location, which is very useful. However, if you combine this with length specifiers, you can control exactly how much is written, which can make this process overall cleaner. So let's explore Format 4 challenge of Protostar, which is one of the harder ones, and use multiple writes to redirect execution to a winning condition. Alright class, this is the demo for Format 4 challenge from Protostar from exploitexercises.com. This is going to be a demonstration of using multiple format string writes to rewrite an address in memory. And what we're going to have to do is use a length specifier to use short writes so that we are more precise, because using format string exploits to, in a single write a very large value is very cumbersome and usually completely infeasible. So the source code is as following. It takes in some arguments but never passes them to a vuln function, which it then calls, and on the stack here it allocates a buffer, and it safely reads in from user input standard in, and then it prints the buffer and it exits right away. So there's no logic going on, and the win function is hello up here, and target I think is just left over. There's nothing to do with that. And what we have to do is redirect execution to void hello. You might see that a different exit is called here. So in the heap demo we just did, we targeted the global offset table with the heap buffer overflow, which allowed us to do an arbitrary write by exploiting how the unlinked macro works. And what we're going to do is use multiple format string writes to redirect the global offset table's exit function, which is located here at 08049724, to the win condition, which is hello. So what we want to do is overwrite the global offset table for entry for exit and point it to hello. So we're going to discover where on the stack our format string starts, and we'll do that with some quick Python. Whoops. parentheses. And let's see, 200s, first, second, third. Here are the 4 ones starting at the 4th index. Now, what we want to do is somehow write this value with a format string exploit. And that gets a little tricky. But we want to start off, whenever you're doing any form of advanced format string exploit like this, is start taking notes. And so we're going to break down byte by byte what these values translate to. So the least significant byte B4 is going to be at going to translate to 180 decimals. We can probably very easily write a string that's 180 characters long and put the amount of characters written so far into an address pointed to the first byte here. So that the next byte in exit will be 08049725. The next byte will be 26. The next byte will be 27, and this will be the most significant byte in exit's address. So what we want to do is overwrite, perhaps byte by byte, the values stored here so that we reconstruct the address to hello in the global offset table. So we hijack the functionality of the exit. Now, So what we're going to do is break down these byte by byte. And so B4 translates to 180. 84 translates to 132, which you can see is shorter than 180. And this is a little bit tricky because we can only expand the amount of characters that we've written and thus expand the total count. We can't really go down, but by limiting it to a short or byte right, we can wrap around to whatever we desire. So as long as the least significant byte here, for whatever we expand it to, is represented in hex by 84, this will be written and should satisfy our needs. So for the hex 184, that translates to 388 characters. 284 is 644 characters. 384 is 900 characters. 484 is 1,156 characters. Then for our other more significant bytes, we run into a similar problem. 04 is simply 4, and 08 is simply 8. And it may be easier just to group them together and look at what 0804 translates to, or hex 804, and in decimal that's 2052. Alright, so in theory, if we group these together, we don't want to target this one. We want to target this because it will overwrite the 27th and the 26th. The first write, if we address it as 24th, will be fine. 25th will write the correct byte there and overwrite any of the additional side effect output from the first one. And I say that because in some cases you could pull this off without the length specifier, simply by just overwriting whatever unnecessary output is produced from this having to wrap around and continually increase till your least significant byte suits your needs. So you can do this without a length specifier and limiting it like that. So what we're going to do is we're going to write the 24th byte, 25th byte, and then the 27th and 26th bytes together and shoot for the highest expansion being finally we will write 2052 characters. So what we're going to do is we're going to start with the 24th byte, the least significant byte address, and we're going to continue And then the next byte, we're going to address, x97, 04, 08, and then finally 27. And now is where we begin expanding things. So far, we have written 3 addresses. Each one of these takes up a character, takes up a byte. So addresses are 4 bytes long, times 3 is 12. So the first one we have to write is 180. So 180 minus 12 is 168. So percent 168 hex, and then what we do is percent the fourth, we'll do a short write, and we're going to write that to the first address we have here, which, as we remember discovering, is the 4th index on the stack is where our string begins. We found that by shooting A's in there first and pushing percent X's after that and counting where it occurs. So that will expand the string accordingly to pull off the first write. Now we have to worry about the second write. So we have to figure out what we put here to expand it such that the rest of this is all going to work. Now let's start with hex 184. Let's pull up a calculator, and so 388 minus what we've written so far is 209x, and then we're going to use the 5th index, and then we have to handle the last one, which is going to be 2052 minus what's written so far, which is 388, which is given up here. And we're going to have to expand this, if this will work, this large, by that much. And percent the 6th index. See what happens. You can see that it seems to be working, at least expanding the string, because it cleared the whole screen, but it is seg faulting. So for the second expansion, let's try the next one, 284. Remember, we're just going for any value that's going to pull this off and have the least significant byte be 84. So what we're going to do is 644 minus what's written so far in the first write, which is 180. So I have 464 now, and we have to recalculate the last one, which is going to be 2052 minus 644, given to us by here. So 1408. Let's see. Nope. Seg fault. So let's keep giving it a go. So 900 now minus 180. We're going to try hex 384. It's 720. So 720. And then have to recalculate the last one. And that's going to be 2052 minus 100 and 1152. Nope, no luck yet. Seg fault still. Alright, so let's try the last one. 1156, given to us by here, minus what is written so far in the first one. So we use 976, and then recalculate this. 2052 minus 1156, 3896. And let's make sure we're printing this all out right. Oh, no, don't print out all possibilities. So the mistake was that we need to escape this $sign, and in the end, it all worked. It's just a minor formatting issue. So what we did, to recap, is planned out what the bytes represent for the address that we want to write, figure out how to attack it, and we had to go about continually trying values that the least significant byte would work for us, and then demonstrated also a 2-byte write and pulling that off with a very large value. And we were able to redirect the execution to hello and win the challenge. Alright, those demos are over, and the rest of the lecture is dedicated to defenses against exploit techniques, and we're going to talk about executable security mechanisms, or as we call them, exploit mitigations. So one of the key questions we're going to ask through this lecture is who should protect what? Obviously, we should expect the developers to write secure code and obviously not have any bugs at all, which is unreasonable. But are there ways to, for bugs that happen to be vulnerabilities, mitigate their exploitability? As we saw that simply just pulling off exploits can be hard. Sometimes even the most mundane things can affect the exploitability of a given bug. For instance, in one of the previous demos, the filler data itself in our exploit actually caused problems depending on what we chose it to be. And that happened to influence the various constraints that were in the code paths that we were basically executing. So are there things that we can instill when compiling a program that mitigate exploits? Are there things that while an operating system is running a process can mitigate various different exploit techniques or targets? And similarly, for hardware, if we remember the debate between von Neumann and Harvard architecture, the main thing with the Harvard architecture is they can distinguish between data and instructions. So let's talk about Linux exploit mitigations. And the first one we were going to talk about is the NX bit. This flag effectively means never execute. It employs the policy that if it is writable, it should not be executable. This prevents execution of any data on the stack, and sometimes the heap, although the heap can be used in, for instance, in C++ and various very object-oriented approaches, sometimes the heap may be executable necessarily. Ways an attacker can bypass this is by reusing existing library code and existing code in the binary, such as return to libc attacks, which I believe we covered, may not have demoed, but will be demoed later. And return to libc came out probably about 10 years ago or so, and it's very, very simple technique, and it completely defeats NX. There are compiler extensions that can protect stack and mitigate stack exploitation. There is Stack Guard, which uses canaries that are basically a random value that's padded before return addresses. Whenever return is triggered, it checks to see if that value is still there. If it's been overwritten, it aborts, prevents the execution of an exploit. However, the GCC team does not adopt Stack Guard, and this only protects the return address in the stack, and there are GS cookies in place instead. Another technique is ASLR, which stands for Address Space Layout Randomization. And the reason I covered the process layout of Windows and Linux memory segments is that ASLR will randomize, depending on the implementation, the starting address at which each segment is loaded in, so it's not easy to reliably point to something in memory. Now, in order to enable it, you have to have a compatible Linux kernel. It was adopted in, I believe, the 2.4 or the 2.6 kernel. I can't remember off the top of my head right now. But if this file proc sys kernel randomized VA space is set to 0, it's turned off. But if it's turned to 1, it's partial ASLR. If it's turned to 2, it's full ASLR. And the contents inside each memory segment are not reordered. They're not randomized at all. It's just the starting address is randomized. Now, there are two main ways to break this, just in general across implementations. There is simple brute forcing, and for 32-bit systems it's much easier because there's less entropy to beat. And then there's finding a mem leak and then doing return-oriented programming relative to a memory location that you know. This technique, ASLR, is very effective and outright breaks any shellcode with hard-coded addressing techniques. And it also breaks return-to-library style attacks unless you have a mem leak into the library. And what you'll find is that for ASLR, when it's set to full, a way to verify that it is running on a given process is to check the proc, whatever the PID, and then maps file is across a number of iterations. You should see that the addresses here should differ per execution for every single segment. For the heap, for the stack, for the VDSO, and etc. However, as I said, 32-bit ASLR does not have enough entropy, does not have enough randomness, and is rather easy to brute force. And if you're trying to brute force a runnable service that is predicted by ASLR, you're probably going to see that activity happen in the middle of the night and when no one's watching, because it could take some time. If it happens in the middle of the day while the system administrator is watching and you don't have someone there overnight, it's more likely to be pulled off. So I should note that for network services, usually the model is that you have the host process listening for connections, and for each connection will fork, and the child will handle the new connection while the server will keep continuing to listen for new connections. This gives advantagers that's not even a word. This gives attackers an advantage because they can bring down the child fork and repeatedly attack it in a brute force attack until it eventually works, without bringing down the service. If, for instance, the host simply handled somehow each connection one by one, a single exploit attempt that failed would perhaps segfault the process and the service would be down, which would be a denial of service attack, but the attacker wouldn't gain access to whatever they wanted. So there are custom enhancements to the suite of Linux security. The PAX Linux kernel patch implements better ASLR, implements better NX, has also more efforts to mitigate other techniques like return to libc, and has more hardenings against buffer overflows, and there's a pretty good FRAC article about it here. GR Security is also related to the PAX team. They partnered up, and the GR Security patch is optimized for web servers and offers very useful hardening features to prevent LD preload attacks, much better ASLR, so on and so on. It's pretty much if you're running a web server or any form of Linux server that is exposed to users, it should be running some form of hardened kernel. and this is a great option. So this blog post from CERT has a really good discussion on the actual randomness of stock ASLR, and if we blow this up and look, that if ASLR is simply set to its standard implementation, you can see that only 1, 2, 3, 4 bytes of entropy are used for the heap. For other libraries, it is perhaps only 1, 2, 3 bytes, and 3 bytes for the rest of this, which is insanely easy to brute force. However, you'll notice that certain segments aren't randomized itself, such as, for this case, they're using cat. Cat is not randomized, and this is over multiple executions of this target process. And the authors went in to investigate that that the GR security and the PAX patches actually don't fully solve these issues. They do improve the entropy. You can see that 1, 2, 3, 4, 5, maybe 6, it's hard to tell, 6 bytes are being used of entropy, which is a huge improvement, but not everything is being randomized, which is a problem. Because I can still hard address in an exploit these segments if, for instance, they're executable, which we know they are. So the author illustrates the effectiveness of a fully randomized process space in that no hard-coded exploit is going to work against this. And it is suggested that you take necessary protections to enhance the weak security mitigations offered by Linux by default. It actually turns out that Windows is perhaps one of the most secure operating systems, although it is perhaps the biggest target on the internet, mainly because of the market share it has and the popularity it has. It still has excellent implementation of ASLR and other techniques. Now, the Windows surrogate or equivalent to NX is DEP, which is Data Execution Prevention. Effectively, you mark anything on a memory page that is writable as also not executable. It makes the stack and the heap not executable, so you can't have any more shellcode there. But you can still have control data there, and still can obviously do return into libc and return to library style techniques. ASLR in Windows is enabled by default in Windows Vista and beyond. That was back in 2007. However, it's only for executables and DLLs that are specifically linked to be ASLR enabled. In other words, the compiler and linker in that phase, in the linker phase, that sets whether or not things are ASLR enabled. And most developers don't know about ASLR and don't know to compile and link things in this way. So there is a registry value that, if you set it, will force ASLR for all executables and libraries. And by default in Windows, the heap, the stack, the PEB, the TEB, we haven't really covered these, and that's fine. You won't be required to know them, are randomized. But there are techniques specific to Windows and specific to Linux and specific to other operating systems to defeat their implementations of ASLR. Sometimes they rely on memory exhaustion, and sometimes they rely on other nuances. So this is by far not a comprehensive coverage of how to beat ASLR. This is for reference. GS stack cookies is a compiler option that adds to a function's prologue and epilogue code to prevent overwriting the return address and other useful pointers. It has been enabled by default in since 2003, and can be disabled. However, it's never recommended. But it allows you to detect buffer overflows that try to target the return address, as we've already stated. So usually you cannot read if say you're exploiting a remote service, you can't read that random value that's on the stack that's protecting the return address. So that mitigates your ability to exploit a stack-based buffer overflow or stack-based vulnerability and target that control flow data, because you have to guess that cookie right. Well, that is something that can be brute forced. Perhaps it would take all night to do it, but that is one way to attack GS cookies. Heap protections in Windows are a bit better than Linux. There's no dlmalloc safe unlink implementation, as we just demonstrated exploiting earlier. And the Windows take on this focuses on hardening the heap allocator algorithm, preventing heap overflows, and implementing safe unlinking. To do this, Windows uses metacookies, a safer unlink algorithm, and it also goes to the efforts of encoding pointers with a key or XORing them as they sit statically in memory. So they're really hard to find, so we can't do that level of debugging to develop an exploit. Just all it does is obfuscates the heap effectively, so it makes it harder to work with. So the other thing that Windows does great is EMET, the Enhanced the Exploit Mitigation Experience Toolkit, whatever it stands for, I forget. It implements better implementations of ASLR, DEP, SEHOP, which is the answer to SEH exploitation and is an effective exploit mitigation that has rendered an entire class of popular Windows exploitation effectively ineffective. It's no longer really a viable nor popular exploitation avenue. That is the realm of SEH exploitation. I covered it last year. The slides from last year, which were very thorough, have been moved to the end of this lecture, and I will not be covering it this time. However, you should note for the exam that SEHOP prevents SEH exploitation pretty damn well, especially when combined with DEP and ASLR, stack cookies, and everything else. RelRow, this basically involves reordering of segments and also the contents of the segments, which makes a lot of exploits very difficult to pull off. Then there's various other mitigations that make exploitation even harder. MemProtect, simulated execution flow, stack pivot, load libraries, heap spray detection, etc., etc., etc. EMET is something that is unparalleled on other operating systems, which I believe puts Windows ahead of the game as far as security goes. It's still the most attacked operating system in the world, as it seems by malware authors. So to recap, the linker and the compiler implement stack cookies. Basically, it has prologue and epilogue, either metadata or code, to make sure that when a return is called, that the cookie hasn't been overwritten, or also called the canary. ASLR is usually implemented by the operating system because that has a large role to play when the process space is all initialized. DEP is the equivalent of NX on Windows side, and there can be a number of different implementations for it. It's either a combination between the linker and compiler and the operating system for software-based DEP, or the operating system and hardware, and we'll get more into this later. Haven't really covered code signing checks. They are extremely effective at preventing exploitation and perhaps the installation of malware on your devices. And that is all we have for today's lecture. We'll pick this stuff up a little bit later in the coming weeks as we now take a break to go into network. And what you need to know about networking for this class.